All right, so I had introduced the concept of a continuous function in terms of a limit last time, right? Do you guys remember what I wrote? I wrote continuity. I said f continuous at x equals to a means the limit as x goes to a of f of x is equal to f of a. So this is continuity of a function at a, right? Now, that's technically speaking not the proper definition, right? Like, proper definition of continuity, which is given here, is in terms of epsilons and such. So let f be a function, a in the domain of f is continuous at a, if and only if for each epsilon greater than 0, there exists a delta greater than 0 for which absolute value of x minus a less than delta implies that the absolute value of f of x minus f of a is less than epsilon. If f is continuous for each point in a set U, then f is continuous on U. If f is continuous at each point in its domain, then f is said to be a continuous function, right? So a continuous function is one for which is continuous at each point in the domain. Now you notice that there's no limit statement in this, right? And although it does look a lot like the condition for limit, you notice there's a big difference. Here, when we define limit, there was a 0 down here, right? Now there's no 0 because we do allow the case x equals to a, right? To talk about continuity, we have to talk about the point itself, f of a. We evaluated a. All right, so continuous continuity does involve the point. It doesn't exclude it, like the limit itself. And there's just a few pictures I should look at here. Let me zoom in a bit. Oh, actually, let me try to zoom in. I'm an idiot. I should be zooming in the other way with the computer. Duh. I should have worn my glasses, is what I should have done. My bad. All right, let's see if I can kind of, oh, stop that. All right, so here's kind of the plain, if the function is continuous, what that means is at the point A, you can look at a green band around the point, and you can fit the graph inside the green band by picking a blue band which is skinny enough. That's what it means for it to be continuous, is there's no like jump in the graph at the point. So continuity means that you can essentially draw the graph without lifting your writing utensil from the page. This is what continuity means. It means that the points that form the graph are sort of like stuck together. All right, they're adhering to one another. Now, that picture only works for the interior boundary point, right? If the point in consideration was a left boundary point, then the graph would look like this, right? So you don't actually have to consider points to the over here because they're outside the domain, right? It's enough that the points in the domain can be fit inside the viewing window, formed by intersecting the green and the blue. So what that amounts to is saying for that kind of left endpoint, you need to require the limit as x goes to a from the right of f of x is equal to f of a. So, for example, oh, wait a minute. Oh, that's a typo. That's supposed to be a plus right there. Yowzers. Ooh, that's a bad typo. Bad typo. Bad typo. So, I will, wait a minute. Yes, typo. That's supposed to be a plus, right? For example, I mentioned previous class, right? The limit as x goes to 0 from the right of the square root of x is the square root of 0, which is 0, right? This describes continuity of the square root function at its left boundary point, which is here, right? So, for example, my apologies, I need to fix, this is a very unfortunate typo. I guess you get what you pay for, right? Let's see here. Now, on the other hand, if it's a right boundary point, oh look, and I've got I apparently had it switched around in my mind when I wrote these notes because I incorrectly have A plus down here too, right? If it's a right boundary point, then you're approaching the right boundary point at points from the left. So this should definitely be a minus right here. That's a typo. A to the minus, because it's this kind of limit if it's a right boundary point. Okay, so anyway, long story short, to discuss continuity, we need double-sided limits at the interior of the domain, but we should approach with either a left or a right limit for like edge points to describe continuity, right? But the basic idea is a continuous function is one whose graph does not jump. All right, so here's the, I have to look at this too. This might have a typo as well. Let me think about this left boundary point. Oh, look at this. I got it right here. It's a left boundary point. We put plus. It's a right boundary point up at minus. So these are actually at odds with the typo. So it really is just up here that this is wrong, right? This theorem is stated correctly. Now, so I'm showing you examples of continuity graphically, right? But it's useful to see how this breaks down at a point of discontinuity, right? Something like this. So this function is discontinuous at that point. Now, to see why that's the case, if you look at the value of the function, which is by the center, the solid dot here, that's where f of a is, right? And you draw this green epsilon band, right? It doesn't matter how much I shrink down this blue band, I can never capture these points down here in the viewing window. They are hopelessly outside the scope of the intersection of the green and the blue band. Like, you just cannot make this small enough to capture these again. That's what the definition captures, is you cannot, it detects a jump, all right? This inequality I'm writing, it's for detecting a jump. And of course, the situation just gets worse with like a vertical asymptote, right? So again, just to recap, a continuous function is one whose graph is drawn without lifting your pen, all right? Now, I should caution that is the slogan we teach students in like pre-calculus, right? It is a little bit misleading in that it really only is true for functions that have what's called a connected domain. If the domain of the function is not connected, if it's got separate pieces, you could still have a continuous function because you could still have the function matching the limit of itself, and the evaluation of the function matching the limit at every point in the domain, and just the point of misbehavior is a point outside the domain, right? So like 1 over x is a good example of this. F of x equals to 1 over x. This graph cannot be drawn unless we lift our pen at the vertical asymptote, right? So, but on the other hand, the point A equal to 0, it's not in the domain of f of x equals 1 over x, right? So it is the case that the limit as x goes to a of f of x is equal to f of a for every a in the domain. Therefore, this is a continuous function. However, its graph you cannot draw with one single stroke, right? Because there's a vertical asymptote. So this slogan that you can always draw the graph of a continuous function with one single stripe of your pen, that assumes a connected domain, all right? So that's, in other words, we lie to people in pre-calculus, but don't tell them, okay? And that's why a lot of the deeper theorems in calculus, especially with continuity, they are based on the assumption that your continuous function has a connected domain, all right? For example, snapshot ahead, we'll talk about derivatives. And one of the results we'll have is that if the derivative of a function is constant, right? Or excuse me, if the derivative of the function is 0, that means that the function is a constant function. That is only true if the derivative is 0 on a connected domain. If the derivative is 0 on a disconnected domain, it could be equal to different constants in different parts of the domain. So you're like, that's kind of fussy. Yes, it is. That's
It is. All right, so here's the problem. Choose a value, we're going to do this one now. Choose a value for C which makes f continuous on the reals, given that, here's the formula. All right, so let's work that out. So just to give you guys a snapshot ahead, what's going on today, I'm trying to wrap up continuity, and we'll hopefully spend the last, probably 25 minutes of class on tangent lines and differentiation, right? That won't be all the time we spend on tangent lines and differentiation, but it'll be the start, so. All right, so I'll put this away. All right. Here we go. ICE 2.5.3. Excuse me. F of x is equal to cx plus 3 for x less than minus 2, right? And it's equal to x squared plus 3 for x greater than or equal to 2, or minus 2, right? This is a case-wise defined function. So let me point out to you some things here. The limit, so a couple different cases. If a is less than minus 2, right, in that case, the limit as x goes to a of f of x, what's it equal to? What's the formula in this case? If a is less than minus 2, the formula is cx plus 3. So plug in a, what do you get? You get c times a plus 3. Fine. That's equal to f of a for any such a. So f is continuous. Okay. I had a problem with the battery on the camera earlier, so whenever these things go off, it disturbs me. But it's fine. The camera's fine. Okay, so f is continuous for points to the left of minus 2. How about points to the right of minus 2? Right? That's the formula in that case. So we can use the limit laws, and we get a squared plus 3. Of course, that is f of a, right? So let me summarize. F continuous on the reals minus the set containing minus 2. It remains to check the continuity of the function at 2. What do we need for the limit? So the question is, does the limit as x goes to minus 2 of f of x equal to f of a? Right? That's the question. What is needed for this double-sided limit to exist? You need what? You need this to be the limit as x approaches minus 2 from the from the left. F minus 2 with upper minus f of x to be equal to the limit as x approaches 2 with an upper plus f of x, right? So this means approaching from the right versus approaching minus 2 from the left, right? And those also should be, those being equal implies that the double-sided limit exists, right? But we need more than that, right? We also need that f of minus 2 matches both of these things, whatever that is, right? So, okay, so what's the limit? Limit as x approaches minus 2 from the from the left. We got what? We have cx plus 3 in that case, right? That's the formula. So this is equal to c times minus 2 plus 3, right? I'm going to call this 1. So this one's 1. This one's 2, all right? Because I ran out of space here. So that's 1. What's 2? Limit, excuse me, x goes to minus 2 from the right. And, okay, so f of x, what's there? X greater than minus 2, we have x squared plus 3 is the formula, right? So we plug in, we've got minus 2 squared plus 3, which is 7. So we need 1 and 2 both to match, right? So 1 equal to 2 equal to f of a. What is f of a equal to? I mean, not a here, but what is f of what? Excuse me, a equals to what? A equals to minus 2. What is f of minus 2 equal to? Excuse me. And I should do the same here. My bad, guys. That was supposed to be minus 2, right? It's this is the a equals minus 2 case we're looking at. All right, so we've got minus 2c plus 3 equal to 7. That's 1 equals to 2. By the way, f of minus 2 is what?
Would that negative 2c be squared? Like it is in
It's not squared.
right there?
That's multiplication by minus 2. This? That's c
Oh,
times.
no, I was looking at the wrong number. I'm sorry. I was looking at this.
Oh, yeah, that's 4 plus 3, which is 7. Now, f of minus 2 is this case. So f of minus 2 is 7 as well. So what do we got? We got minus 4 equals to 2c, right? So c equals 2. Minus 4 over 2. C equals 2. Minus 2. So we have to choose a constant of minus 2 in order for this to be a continuous function on the reals. Now we could change this problem a little bit and make it even a little bit more interesting. Like you could add another variable if you wanted to. If you wanted to modify this problem just a little bit. First of all, do you guys understand the problem as stated? No? No? Mm-hmm.
I have a question. Why is it from the right there and from the left there? Like negative to positive to.
Yeah, from the left here and from the right there.
Yeah.
Because in order for the double-sided limit to exist, we have to have both this and that. Both have to match up in order for this to exist, right? Like the left and the right limits both have to separately exist and match in order for the double-sided limit to exist. So that's why I have to look at the left and the right. because there's two cases. Look, guys, we could modify this function ever so slightly, and let me do it over here. We could like g of x, cx plus 3, x less than minus 2, x squared plus 3 for x greater than minus 2, and then we could put b for x equals to 2, right? I regret using that blue chalk. I don't know if you guys can see it. Can you guys even see it? You guys can see it. I don't know if the camera can see it. Yeah, no, it kind of shows up. Look, so
can you switch those two? Like, can that one be positive and that one be negative and stuff? Like, doesn't matter.
well, the left and the right limits have to match up. I mean, so graphically, what's going on here? All right, so at minus 2, you know, we have a line for x less than minus 2, right? And x squared plus 3, it starts at 7, right? And it goes up like this, right? So if you were to continue, this is y equals x squared plus 3, right? It's a parabola which opens up, right? But this is a case-wise defined function, so we're just taking those values, minus 2, and that away, right? Now, cx plus 3, that is a line with y-intercept 3 and slope c, right? So like the y-intercept is 3, right? And it has slope c. Now, in order for this to be a continuous function, you got to have these meet. And so that's why we had to choose c equals to minus 2 to get that negative slope. Hey. Did I make any arithmetic mistake? Probably a problem. It may be a problem with my graph being too sloppy. Let me think about it for a second here. Oh, C is definitely minus 2. If I plug in, yeah. Oh, I'm an idiot. The y-intercept was what? 3. Not a bit. Why did I put the y-intercept for the line up there? I'm a dummy. So the y-intercept's down. The y-intercept for this and this are the same, you know? So the line has to look like this, roughly speaking, in order to match this point right there, right? So we're going through the left and the right limits matching to make the function's different cases glue together at the gluing point. That's basically how these work. If you have a case-wise defined function where the separate cases are just like polynomials or just they're formulas which make sense without question in the cases they're defined, then you're going to get automatically that the function's continuous at points away from the gluing point, like we saw here, right? F is continuous away from the gluing point. And then the issue really is just how do you make the different cases glue together, right? Now, my blue one, I was throwing an additional wrinkle, which is to say, like, suppose that, you know, you've got, you've got the line, right? Actually, you can to choose a different value of c, you can make the line look like that, right? If you choose the wrong c, you can make the line come up to here. Like if I choose minus 3 instead of minus 2, the line wouldn't meet the parabola where the gluing point is, right? And if the value of the function is b, like I could define the value of the function to be whatever. I mean, I could make f of minus 2, I could put b equal to, 3, like that. Now, obviously, that wouldn't work, right? f of minus 2 in that g of minus 2 would be 3, and that would not be equal to the left and the right limits. Even after if I make my c equal to minus 2, as we learned, that will make the line and the parabola match up, right? But I would also need to choose b equal to 7 in order to put the gluing point where it's supposed to be, right where the cases meet. Okay? So anyway, I don't think I have a problem like that in your homework. It just occurred to me that's a way we could make this problem slightly more interesting. Any questions? So to summarize, there's a homework problem like this in your homework. What you want to do is look at the left and the right limits at the gluing point and make them match up. That should allow you to choose the value in the formula to make it be continuous. Okay, let's move on here. So theorem 2.5.4, we have let f and g be continuous at, let's say, x equals to a. All right, I usually just say at a. And let's let c be a real number. All right, then we get the following. Number 1, f plus g is continuous at a. 2, constant times the function is continuous at a. 3, the product of the functions is continuous at a. And 4, given g of a not equal to 0, f over g continuous at a. All right? So this is, let me put this theorem into words. What's it say? It says if you have two continuous functions, right? The sum, the scalar multiple, the product, and even the quotient of those continuous functions is once more continuous. Now this makes a very simple kind of test proof question that's like, not a bad question. Let me show you one. Actually, which you guys choose? Which one do you want me to prove? Student's choice. Just not 2. It's boring. I said just not 2. How about, so 4, okay, so, all right, so we're, suppose g of a is not equal to 0, right? Consider the limit as x goes to a of f of x over g of x, right, is the limit as x goes to a of f of x divided by the limit as x goes to a of g of x. Now, the reason that I can make that step, the reason that the limit law for the quotient applies here is because I know what I wrote on the right-hand side. Those are both limits which exist. Why? This is equal to f of a over g of a, since f and g were assumed what? Continuous at a, right? And what is f over g, f of a over g of a? And we also knew, and g of a was not 0, right? So this, by definition, that is f over g of a, right? If you're talking about the f over g function, its values are defined by dividing the f value divided by the g value. That's how we do the quotient of functions, by the pointwise rule. There you go. That proves that f over g is continuous at a, because the limit of the function is given by plugging the limit point into the function. The proof of 1, 2, and 3 is literally the same. Apply the limit law for the sum, the limit law for the scalar multiple, or the limit law for the product of functions. Immediately they yield continuity of the sum, the scalar multiple, and the product. The next result is that if f is continuous at a and g is continuous at f of a, then g composed with f is continuous at a. All right? Okay, so proof. You basically assume the conditions of the theorem, consider the limit as x goes to a of g composed with f, right? So how does that work? That's the limit as x goes to a of g of f of x, right? That's what that means. Composition of functions. Now, we had a limit law about composition of functions. And the limit law said that if, well, basically this is what the limit law says in this context. It says that this is equal to g of the limit as x goes to a of f of x. This is by limit law. By limit law for composites. But what is the limit as x goes to a of f of x? Well, that is equal to f of a, because we're assuming f is continuous. So this is f of a. So we have g of f of a, which of course is g composed with f of a. So that proves that g composed with f is continuous. So the composite of continuous functions is continuous. All right? So let's think about this. What are elementary functions? Remember chapter 1? I had a laundry list of elementary functions. Polynomials, sine, cosine, algebraic functions, exponentials, hyperbolic functions, and inverse functions of all of these. Actually, all of these are going to be continuous on the interior of their domain. And the proof of that, like essentially these, the theorem I have on the board right now proves like a good chunk of it. You also need to prove, that sine is continuous, that cosine is continuous, that the exponential is continuous. And there's what's called an inverse function theorem. You can argue that if a function is continuous, then it's invertible, then the inverse function also has to be continuous. All right? So let me give you a couple examples here. Absolute value of x minus 3, right? Here we have the limit as x goes to a of the square root of the absolute value, excuse me, I'll do it symbolically here, f of x limit as x goes to a of the square root of x minus 3 squared. All right? This is a formula for the absolute value, right? It's the square root of the square. Okay, so what do we know? Well, we know that the square root is a continuous function, all right? The square root is a continuous function. So we can look at this. This is like a composite of the square root function, and the x maps to x minus 3 squared function, right? The outside function is square root. The inside function is subtract 3 from x and square it, right? It's the composite of those two functions. And so I can use the composite limit rule and say, well, that's the square root of the limit as x goes to a of x minus 3 squared, right? Now, what's the limit as x goes to a of x minus 3 squared? Well, you may or may not remember this, but one of the things I told you guys last time is like the limit of any polynomial is what? If p of x is a polynomial, the limit as x goes to a of a polynomial of x, what was it equal to? It was equal to, you just take the function, you take the polynomial and you evaluate it a, right?
So it'd be a minus 3 squared.
Exactly, so the square root of a minus 3 squared.
Then we could just get a minus 3.
Well, careful. If a minus 3 is negative, you get 3 minus a. So this is the absolute value of a minus 3, which is good because that's f of a. So this argument shows you what? What does this argument show? This argument shows that f is continuous on R. Since a was what? Arbitrary, right? So if you had f of x was equal to like 3 sine of x plus 2 cosine x, then the limit as x goes to a of f of x is the limit as x goes to a of 3 sine x plus the limit as x goes to a of 2 cosine x by the adding limits rule, right? But what else can we do? We have the property, we can pull constants out of the limit, right? So I can take these, the 3 and the 2 and pull them out, right? So I can take this 2 and bring it out here, right? I bring this 3 and bring it out here, and so I get 3 limit as x goes to a sine of x plus 2 limit as x goes to a cosine of x, right? Now, there's a theorem that sine and cosine are continuous, all right? So theorem, sine and cosine are continuous on R, right? So if you know that, that means what? You just plug in a, right? You got 3 the sine of a plus 2 the cosine of a, and then what do you got? What is that? Well, that is f of a, right? Which shows you that 3 times sine plus 2 times cosine is also a continuous function. So like if you know that the basic building blocks are continuous and you know limit laws, you can prove that sums, linear combinations, if you will, of those continuous functions are again continuous. Now, I have not proved that sine and cosine are continuous, have I? I said it was true, right? I mean, you guys know what the graph looks like, right? This is sine, right? Seems reasonable to say that that's continuous, right? But the actual trouble of proving it is, it's non-trivial. It's actually kind of a pain to prove sine is continuous, and the same is true for cosine. Although sine and cosine are related by a simple shift. So if you get one as continuous, you can get the other using some of the other theorems we have here. All right, so next up here, continuity. Let's talk about what I call the inverse function theorem, right? So the theorem, oopsie, my bad. I keep forgetting to. I say I tried to go before the fall, right? Like I can do my own camera work. I got it. I got it figured out. Do I? All right. So here's the continuous function theorem is very simple. Theorem. If f is continuous with inverse function, f inverse, then guess what? F inverse is continuous. Now I think as I have this theorem stated in the notes, I have probably cluttered it with some kind of technical details. But this is it, all right? To actually prove this, it's pretty involved, but I think we can argue for the plausibility, right? So, and this is also a good chance for us to review. What does it mean for a function to be? So here's a proof sketch, all right? And I do mean sketch. It's very sketchy, my proof here, all right? So what can you tell me about a function if it's going to be invertible? What's the graph of the function have to look like? How about this? Could this be an invertible function? This is not an invertible function because it's not a one-to-one function. It fails the horizontal line test, right? So an invertible function has to be one which passes the horizontal line test, right? You only get, each y output that it attains just once. So let's see here. Let me go with a function that we like, the exponential, right? Here's y equals f of x. That's the exponential function, right? Just now, it's definitely a very proof by example. Great. Okay. Not really. What does the inverse function to the function look like? What do? You take the line y equals x, right? And you reflect the graph of the function about the line y equals x, right? For each point here, let's say a comma b, you trade it for the point on the other side, right? B comma a, right? A lot negative, a little bit positive, a little bit positive, a lot negative. Flippity-floppity, right? And this is how you graph the inverse function. You reflect across the line y equals x. So think about it. If the original function is continuous, right? If the values of the function are glued together nicely as you look at the graph, is there any conceivable way that that process of reflecting across the line y equals x can spoil the adjacency of points on the graph of the inverse? If you think about it, no, the points are still going to be glued together nicely. So certainly, yes, the inverse function should also be continuous if the function is continuous, right? Now, I think in my notes and in the appendix, I spend considerable technical effort to prove that. It's not a simple thing to prove, but it can be proved using epsilons and deltas and all that stuff. So well, what does that matter? Well, here's why it matters, because inverse functions are extremely important for understanding the formulas that we hold dear. Like x to the power p. How do you define x to the power p? Ever think about this? Let's keep it simple for x greater than 0, all right? All right, so let me just warm up here. If you look at f of x equal to, say, x to the, 13 fourths, you could look at that as the fourth root of x to the 13, right? So rational powers of x we can look at as the composition of like a powering to some integer power followed by a root, right? Agree? And so we can discuss continuity of that using the fact that we know the root function's continuous and we know like the power function's continuous, and so it's a composite of those two things, therefore x to the power p is continuous. And when I say power, I meant integer power. But what about x to the pi? What does that mean? How do we define x to the pi? You guys ever think about this? How do you do that? Like, pi is not a rational number, right? It's not the ratio of two integers. It's 3.1415 blah 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 blah, never repeats, right? It's not a rational number. So what do we mean by that? Well, here's what we mean. This is equal to e to the pi times the natural log of x. That's actually the definition of x to the pi. So, or it's a potential definition anyway. We can define non-rational powers playing this game with the exponential and the log. See how this works? If I have like x to the p over q, it's, well, let me shut up. All right, so anyway, that's how you define it. So check this out. The limit as x goes to a of x to the p, right? It's the limit as x goes to a of what? Well, x to the p, remember, is e to the p times the natural log of x. That's how we define x to the power p when p is not rational. The inverse function theorem says if you know exponential is continuous, I guess we haven't proved that either, but it's true, exponential is continuous. The inverse to the exponential is the natural log. It's also continuous. X to the power p is formed by a composition of the exponential function with scalar multiple p of the natural log function. And then you can use limit laws. See, this is equal to e to the limit as x goes to a of p ln x by continuity of exponential. And the composite of limit laws, we can pull the limit inside the... Basically, this is one of the rules for continuous functions. A continuous function, if you have a limit of a continuous function, you can pull the limit inside the argument of the continuous function, provided you're at a point in its domain where that makes sense. There's a truckload of homework problems that you can solve using that idea. But maybe I haven't made too many like that, actually. But anyway, then what? Well, how's this work out? Well, that gives you e to the p times the natural log of a. Assuming, of course, that we're assuming from the outset, what about a? We're assuming a is positive, right? So then we have e to the p log a, which then by definition is a to the power p. So in other words, the limit of f of x is equal to f of a when f of x is x to the p. X to the power p is continuous. We know that because we can argue that the exponential and the logarithm are also continuous. All right, anyway, I think I've shown you enough about continuity of functions. These are games we can play. And the long and short of it is our whole lexicon of elementary functions, sine, cosine, algebraic functions, hyperbolic sine, hyperbolic cosine, all of these things, they're built with formulas that are just sums or compositions or products or divisions of basic building blocks which themselves are continuous. Therefore, by the limit laws, we get that all of those functions are continuous on the interior of their domains. Which really just goes back with what I said last class, which is like when you're calculating the limit, you get to the point where you can plug the number in, then you just plug it in, right? Once you've removed the indeterminacy, the expression you're looking at is then the formula for a continuous function, so you can just evaluate. But of course, before that point, you have to watch out for division by zero. I am a little short on time, so I'm skipping in-class examples on page 73, which means what? You can do them. You can add, and you can add examples there for what? Bonus points. Yeah, that was the rule. So what's left in the continuity chapter is one section, which is the intermediate value theorem, right? I'll be brief about this. I've given you a couple homework problems about it. This is another one of those things that we can prove it. The proof of it really rests, and sometimes I do. The proof of this, the intermediate value theorem, rests squarely on the completeness axiom of the real numbers. So the completeness, remember, completeness axiom was like every non-empty set which is bounded above has a least upper bound, which is kind of this technical kind of sounding thing. And essentially, the least upper bound, it says that there are no holes in the real number, right? But here it is, the intermediate value theorem. Which we will forever more abbreviate as IVT, all right? Says if f is continuous on, excuse me, closed interval from A to B, and n is between f of A and f of B, then there exists C in A to B such that one moment. I feel like I'm, yeah, I'll say open interval from A to B. C in the open interval from A to B. I knew that felt wrong. Open interval from A to B, such that f of C is equal to n. N is that intermediate value we're talking about, all right? There exists so this n right here is the intermediate value that's being named in the theorem. So they're kind of like, well, there's a lot of things that can happen. Here's two possibilities. All right. That was, it's supposed to pass the vertical line test, all right? So I know it's a little sketchy, but the point is, here's possible graphs, right? What does n look like? Y equals to n. Could be like here, right? So, whoop, right there. That's the C, such that f of C is equal to n, right? Does the theorem say there's just one? It does not. So over here, this one, if this was n, right, you see we've got a C1, a C2, a C3. F of C1 equals F of C2 equals F of C3 equals to n. This is the intermediate value theorem. So I'll show you ice. Show there exists solution of x to the 5th plus 4x squared equals to 100. All right. Notice that the intermediate value theorem does not tell us how to find C. It just says that it's out there, right? It's out there. And that's this question. This question doesn't say find the solution. It says show it exists. So the intermediate value theorem is the tool to go with. So what do you guys think? Well, first of all, as you look at this problem, right, can you solve for x anyway? Could you solve that for x? This is on page 75, 2.6.3. I mean, I personally cannot solve for x. There's a very select class of fifth order polynomial equations that I can just do some kind of, like, some sort of ninja algebra move and solve for x. Like, it is not likely. So how are we going to show that this, how about this? How about this? So here's how it goes. We're going to name names. We're going to call this f of x, right? This is continuous on the reals, right? It's continuous everywhere. Certainly, the intermediate value theorem applies, right? So, let's see here. How about f of 0? What's f of 0 equal to? 0, right? 0 is less than 100, right? So can you tell me something I can plug in and get a number greater than 100 for f? Make it something easy to calculate. How about what if we 10? Ah, good choice, good choice. That was the correct guess. I'm joking, of course, it's a guess, right? So 10 to the 5th plus 4 times 10 to the 2nd power, also known as 10,400, right? And that is definitely greater than 100, right? 100 is an intermediate value. So thus, by intermediate value theorem, there exists C in 0 to 10 such that, C to the 5th plus 4 times C squared equals 100, aka x equals to C solves, x to the 5th plus 4x squared equal to 100. There you go. Now, this is actually the bedrock on which our whole sign chart method is resting, right? The sign chart method, if you go back and think about it, we're solving inequalities. We're trying to decide where's the expression positive.